So it's my pleasure to introduce Justin Hodgkiss, who is director or co-director of the MacDiarmid Institute for Advanced Materials and Nanotechnology and a professor in physical chemistry at Victoria University. MacDiarmid Institute comprises scientists and investigators from 7 institutions who combine their expertise to find new ways to positively transform people's lives, which I think is a great thing to be happening in this modern day when scientists seem to compete with one another. The institutions include 5 New Zealand universities: Auckland, Massey, Victoria, Canterbury and Otago, along with Callaghan in Innovation and GNS Science. The Institute focuses on materials science and new technology, bringing together the fields of chemistry, physics, biology and engineering. They work to understand how to make specific materials more energy efficient and to take that through to the practical design of materials to avoid toxic and scarce elements. They also collaborate to bring innovations to the marketplace where they can help address the big problems of our time and contribute to the New Zealand economy. Justin's research group has pioneered ways of manipulating laser pulses to understand, for example, how solar photovoltaic cells convert light into electricity, or how the skin pigment melanin protects us from UV light. I'd be fascinated by that sort of stuff. Processes which occur in picoseconds. That took me searching Google to find out that a picosecond is 1/trillionth of a second, which is sort of hard to imagine, really. It's a bit like $1 trillion. Justin is a founding inventor for startup Advemto, which is commercializing laser instrumentation his group invented, and he's passionate about helping other scientists to commercialize their research discoveries. Justin completed his undergraduate studies at the University of Otago before undertaking his PhD at MIT in the USA, postdoctoral research at Cambridge, and returning to New Zealand in 2009. The subject of his presentation today is materialising a sustainable future. Over to you, Justin.
Oh, kia ora. Thanks, Mick, for that introduction. And actually, when you were introducing the work we do in the MacDiarmid Institute and the priorities, that actually sounded like a pretty good introduction to the talk that I'm giving today. Essentially, what I'm going to be doing over the next half hour is just kind of giving you some examples of really what we mean by that, of what we mean by materials that can have a positive impact on our sustainability. Okay, is that coming through?
Yep, that's come through.
Okay, I'll just put it onto. You see it in full screen now? Yep. Okay. So thanks again for the invitation. I really do enjoy getting out and giving these kind of talks. So thanks again for having me along. And I gather that some of you may have heard of a variation of this at a previous event last year. So we all know about some of the environmental problems that the Earth is facing, from air pollution, water pollution, and a lot of other water-related issues in New Zealand right now. Of course, plastics in the environment is a big issue, microplastics, and of course the big one, the big issue that we're really facing is climate change. And you will know that this week there's the New Zealand government has put out its emissions reduction plan. And a couple of years ago, we committed to being carbon neutral in 2050. And one thing that's clear in the emission reductions plan and everything else that you've read from the government's position is that we can't really get to carbon neutral by 2050 without innovation. And I guess my message today is that that there's a lot of potential for innovation that will really address some of these problems in quite a meaningful way, as long as people's mindset and behaviors change along with them. So whether it's replacing plastics with biologically derived sustainable alternatives, whether it's electric vehicles and the associated battery technology, or harvesting solar energy, even sustainable fertilizers, superconducting magnets for wind turbines. These are all things technologies that will make a significant difference, and they're all technologies for which it all comes down to the functional properties of materials that they're made of. And that's really what the focus of the MacDiarmid Institute is. So I'm going to, for the first half of my half-hour talk, I'm going to, or maybe a bit longer than half, I'm going to just dive into some examples of research that it's happening in the MacDiarmid Institute that really just show you how our work spanning chemistry, physics, biology, engineering on developing new materials is actually impacting each of these areas. And I'll range from some quite tangible things to some quite out there things. And then I want to show you at the end, I want to just give a few examples of a few startup companies in New Zealand, local companies, just to show you that this is not just some kind of pipe dream thing that we're working on in universities. It's really happening, and it's really quite exciting. Okay, so this is the first example that I'd like to share. So I'll just be running through lots of different examples, basically. So you can sit back and relax, and of course I'll be around to take questions at the end. So this is Professor Sally Brooker from Otago with some of her PhD students, and she's holding up some corn in a plastic drinking cup. And the drinking cup is made out of a bioplastic that's basically made from mushed up corn. That's from which you can derive some monomers. And basically what Sally's group have done is, in collaboration with researchers overseas, they've made a catalyst that takes the molecules that you can get in abundance from corn, and it makes them into a biopolymer that both biodegrades and is bioderived. So it's not made from petroleum. So this is a big area of research, replacing petroleum-based, if we're looking at getting away from oil and fossil fuels for energy, we also want to get away from depending on them in the chemical industry, including in plastics. The next example is from my own research, and it's also plastic related, but in this case it's plastic solar photovoltaics. So the picture that you see on the left is actually a solar photovoltaic cell. So it absorbs light and creates electricity. And I can say to this audience that, it probably looks like a photographic film back from the old days. When I speak with school students nowadays, they have no idea what I'm talking about when I make that reference. But I'm old enough to remember. And yes, it is. It responds to light and creates electricity, and it's very different to the solar panels that you would see on your roof, which are kind of like panes of kind of purpley blue glass almost. They're solid, and what we're working on is making these solar photovoltaics that use polymers as the active medium, and that means that they can be printed and potentially manufactured extremely cheaply. So the reason I've got a picture of a bag of potato chips up there is to remind me to say that a chip wrapper is actually layers of different plastics and foils, and it's actually really the same as this photovoltaic. It's just different layers of polymers and foils. But you'll know that you don't need to be in Silicon Valley to be manufacturing potato chip bags. This is actually something that could be manufacturable, in the hut. And, there's lots of places around New Zealand that manufacture packaging. And it's really something along those lines that could actually be used to generate photovoltaics, which is a electricity generation. And the other picture down in the bottom right is a picture of the laser in my lab that Mick mentioned in the introduction. So this is, you can't actually see the pulses the way that the photograph is taken. But when you see this beam of light shining through, that's actually comprised of pulses that are not only femtoseconds, but actually picoseconds. Sorry, they are femtoseconds long, which is 1,000 times shorter again than a picosecond. And we do that so that we can kind of take pictures of what happens when this thing interacts with light, and we can kind of almost make like a strobe movie of how this material turns light into electricity. That's what we do in my lab. And you don't need to look at all the details on this, but what I'd like to show you, I'm going to zoom in on the next slide. This is a plot of all of the different types of solar photovoltaic cells that exist and their efficiencies over time. So if you look through the middle of this plot, all of the kind of blue colored, that's the standard technology that you see on your roof, silicon. And if you look down in the bottom right corner, which means that things that are happening more recently, you'll see a bunch of red curves, and they're rapidly catching up with the blue. So I'm working on the red, which are these polymer-based technologies, and you'll see that their efficiencies are kind of going up in steps. Right now, in fact, right now, this isn't even up to date. Right now, the record efficiency is almost 20%, compared with about 26% for silicon. So actually really closing in on silicon quite rapidly due to development and discovery of new materials that can be manufactured much more cheaply. So there's the laser beam again. So I want to switch gear a little bit. So it's one thing to capture solar energy and generate electricity, and ideally do that very cheaply. But whenever you have a renewable energy source, whether it's solar or wind, it really becomes much more valuable if that is, if it's coupled to some kind of storage system to mitigate the energy fluctuations from when the sun isn't shining or when the wind isn't blowing. So there's a number of researchers in the MacDiarmid Institute working on grid scale batteries, whether that's lithium-ion batteries, but really big ones, or whether it's lead acid batteries even, which are basically like old car batteries, but other types of batteries, which I'll mention in a second as well. So there's a push, for example, in electric vehicles. So electric vehicles, EVs, they use lithium-ion batteries. And of course, the batteries themselves are the things that are the most expensive and the things that we worry about with respect to sustainability. Access to lithium as well as other elements that they need a lot of, cobalt, for example. There's also geopolitical concerns with those elements. So one area of research that we have is replacing lithium in the lithium-ion battery. So the battery works when the lithium ions move around between the electrodes. But we have a research program on aluminium-ion batteries, and theoretically, these can be even more efficient and have a higher energy density than lithium. And that's because each aluminium ion has 3 times the amount of charge as a lithium ion. So an aluminium 3+ ion moving around, one ion does 3 times as much work, more or less, as a lithium ion. And I'll come back to where this research program is at the end of the talk. And another area of battery research is in so-called flow batteries. So for most batteries that we know of, lithium-ion batteries or just the AA batteries or whatever, they're solid materials. So we have a solid electrode. A flow battery uses dissolved electrolytes, and those are the things that kind of store the charge. And to extract the charge, you flow the electrolytes to a membrane where it can transfer electrons or charge. You would never use one of these in an electric car or something like that because you need a big tank of the electrolyte. But actually for let's say grid storage, if you just want to store energy to, smooth over fluctuations, as long as you've got a bit of space to have a tank, then they're actually a very, very cheap way of storing energy. So this is a researcher of ours, Professor Aaron Marshall from Canterbury, who's an expert on redox flow batteries. And they're very, very simple. They're very, very, very cheap. And if you need to store more energy, you just have bigger tanks. So as long as you've got space, and it's not going to be in your car, it's going to be in some industrial plant somewhere, then you just store more power with more volume. And if you need to increase the output power, the amount of current, then you're just pumping more of the liquid through. So it's actually kind of a low-tech solution, but one that's of great interest now. So you've probably also heard a bit about the hydrogen economy. And the reason that that's really of a lot of interest is because if you take hydrogen and you burn it in air, then you get energy. And water is the only byproduct. So it's completely green. And to go back the other way, if you put in some green energy, let's say from solar or hydro or wind, then you can kind of pump the energy back in and go back the other way to get hydrogen. You don't need to burn it. You could, in fact, more commonly, you would use a fuel cell to get the energy out. So you would get a current out. But of course, it's not just carbon neutral, it's carbon zero. There's not any carbon involved in this cycle whatsoever. But there's a lot of materials challenges to bring this to fruition. And many researchers in the MacDiarmid Institute are working on it. So for example, there's the electrode materials that you use to so-called split water. You put in green electricity, you split water to give you hydrogen, and oxygen would be the other thing that comes from that. We need electrode materials for fuel cells. We need catalysts. We need membranes in fuel cells. If we're going to replace, let's say, our gas network with a network of hydrogen gas around the country, we're going to need a lot of things like hydrogen sensors to detect hydrogen leaks and that kind of thing. So there's a lot of work going into the kind of supporting technology around a hydrogen economy. An interesting project is led by my colleague Chris Bumby at the Robinson Research Institute here in Wellington. And he's working on kind of industrial applications of hydrogen. So as well as, transport and electricity, a really big application of hydrogen is in the manufacture of steel. So currently, steel is responsible for a huge amount of carbon emissions because as well as burning coal for the energy of making molten iron, the carbon is actually chemically used as well. So it's actually chemically used to reduce the oxidized form of iron. And so as well as needing a new form of energy to melt the iron, you actually need something to act as a reductant, to give it electrons. And so that's where hydrogen comes into play. And so this is the alternative reaction where you take hydrogen plus iron oxide to give you metallic iron and water. And so Chris Bumby is leading a significant project taking iron from North Island, from Taranaki iron sands, and reacting them with hydrogen in a iron ore reactor to make a completely carbon zero iron steel making process. And the results for that are very, very promising. So another change of gear is around porous materials. So around 10 to 15% of the world's energy is used doing chemical separations. So for anyone who has any background in chemistry, this is things like distilling, making fuels, it's just separating out different fractions of petrol and diesel and things like that. Takes a lot of energy. All of the fine chemicals industry, fertilizers and things like that. Generally, you need to put in a lot of heat in order to separate things out. But if we could do all of these things at low temperature, as an ambient temperature, like room temperature, or close to it, and at low pressure, we would save a huge amount of energy. But to do that, you need to kind of exploit different properties of molecules other than their boiling points and things like that. And so we've got a large program of research that's on porous materials that are basically molecular scale filters. So they will let some molecules through and not others. And one example of this is these so-called metal organic frameworks, whose pores can be tailored to soak up CO2 and to let other gases pass through. And this is not just a case of soaking up CO2 from, say, emissions, but actually capturing the CO2 in a form that you could then apply some other chemical reaction, some catalysis, to convert that into something else rather than letting it go into the atmosphere. So this is research that's led by Professor Shane Telfer, who's one of our Massey University investigators. And so again, another change of gear, and this is to another really major source of energy consumption globally and in New Zealand, and that's the energy cost and therefore the carbon cost of computing. So every time we send an email, play Wordle, watch a cat video on YouTube, it's actually taking up a lot of energy, not just on our phone, but in data centers somewhere in the world run by Facebook, Google, Apple. There's a huge amount of data processing that goes on to support the cloud, the internet. And you'll see data centers like this is in Finland or Sweden or somewhere up near the North Pole. And the reason that it's there is because it's so cold that you save on air conditioning. So when you've got, loads and loads of computers, of data servers in a room, generates a huge amount of heat. And so it's just much easier to keep them cool when it's freezing cold outside. But even when you do that, it still costs a lot of energy. So it's been estimated that each Google search costs between 1 and 10 grams of carbon, of CO2. And Google searches, over time that they've just become a lot more powerful. So they're actually drawing on a lot more data. Another fact along those lines is that even before COVID, the energy cost, or the carbon cost rather, of computing had exceeded that of air travel. So even before we all stopped traveling with COVID, the carbon cost of computing was higher than that of air travel, which I think is pretty staggering. And it's something that's kind of invisible to us when we're just sitting on our computers. Even the Zoom meeting is not entirely carbon neutral from that perspective. So another area of research that we have in the MacDiarmid Institute to address this, actually, no, before I get to that, just a little diversion. So this is 1997. Garry Kasparov, world chess champion, being beaten in chess by Deep Blue, the IBM supercomputer. And that's on the right is Garry Kasparov accepting his second place in that match, very ungraciously by the looks of it. And from the looks at the sign, it says it's the rematch. So yes, in 97, a computer beat the world chess champion. But then in 2017, there was an even bigger landmark, and that's that a computer learned how to play chess. So this is using artificial intelligence. It learned how to play chess, and then it became the best chess player in the world in 24 hours. And so, just from, it's obviously computationally a massive task to kind of search that parameter space and try different moves and learn from the outcomes. But that's really a glimpse of artificial intelligence. And of course, the other side of that is that artificial intelligence, which is important in all of the algorithms that we deal with, whether we know it or not, takes a huge amount of data processing. So interestingly, our brains, which artificial intelligence is kind of trying to replicate in a way, our brains are intelligent, but they actually don't take a lot of energy. Our brains, I think, are about, if you just look at the power consumption of a brain, which is the energy per second, our brains are something like 10 watts or something like that, which is in the old type of light bulbs, not the energy efficient LEDs, that would be like 50 to 100 watts would be a standard light bulb. So a brain, actually, in terms of energy consumption, is a dim light bulb, at least mine is. So they actually, but brains are quite remarkable for something that takes such little energy in terms of pattern recognition and sophisticated analysis. A brain is quite remarkable. It's not so remarkable at doing, let's say like spreadsheet type calculations. It's not going to be anywhere near as effective as a really simple, a really basic calculator that doesn't take much energy at all could beat the brain. But for more complex like pattern recognition, a brain is, just from a purely physical perspective, a brain is really remarkable. But a brain doesn't work anything like a computer. Computers is all binary operations, zeros and ones, and logical operations derived from zeros and ones. And zeros and ones are great for kind of doing maths, but for doing more complex tasks like pattern recognition, a brain is really well suited. And a brain is kind of a network of different nodes, which are neurons. And basically, there's a really complex pattern of connections between those neurons that changes over time as well. And so you get this kind of this really complicated network effect between the input and the output. And so what I'm getting to say is that we've got researchers who are working on developing new materials for computing to address this problem of the high computational thirst for computing materials, but materials that think more like a brain. And so this is an example from Professor Simon Brown from Canterbury, and he's looking at nanoparticles that kind of form these random, they're literally random, they're just sprayed and they land where they land. But when they're random, you get different combinations and different patterns of different pathways and networks between them. And what they find is that, that's a picture from an electron microscope. What they find is that when you wire up electrodes and you look at the way they call them spatiotemporal correlations, it has all the signatures of what you see in the brain. And so Simon and his colleagues are making kind of computer chips out of these materials and getting them to do tasks like speech recognition, vowel recognition, and things like that. Okay, so that's the end of the main part of the talk, where I just give a few examples of where material science is kind of tackling some of these sustainability issues. But I want to end with a few examples of where the rubber is hitting the road in New Zealand, and that is with startup companies that are in the sustainability technology sector. And this is a message that I give whenever I speak with school students who are thinking about what to do at university. And that is that the New Zealand tech sector is growing at 10% year on year. And it has been for quite some time. But now the scale has got to the point where it was already going ahead of tourism as an export sector. Even without COVID, it would have, around that year, it would have become more economically important than tourism. And within a couple of years, it's expected to go ahead of dairy as well. and be New Zealand's #1 export sector. And this is just something that not enough people know. And on top of that, it's a sector where there are good jobs. This was Sir Paul Callaghan's message. We want industries where there's a really high salaries and high revenue per employee. And it's not just the jobs for the scientists, but all of the associated service employment. And these, I'll give you some examples of some of these companies that you may or may not know, but they're in biomaterials and space, biotechnology, Māori economy. There's so much going on. And I guess another part of Sir Paul Callaghan's message was that we don't actually know a lot about these companies because they're export focused. The way that they create value and make money is identifying a niche opportunity that's got a global market. So they're not necessarily going to be household names in New Zealand. The market might not be in New Zealand at all, as in the company Advemto that I'm a founder of. I doubt we'll sell a product in New Zealand, but there's a lot of people around the world that are keen to buy them. So I'm just going to run through a few examples of spin-out companies that are doing really cool things, and hopefully you'll hear more about them in the future. The first is a company called ZINCOVERY that spun out from University of Canterbury and the MacDiarmid Institute. And their technology is about recovering zinc from waste. So particularly in the galvanizing industry, where zinc is used, you have to pay money to dispose of this really toxic, nasty waste, which is a mixture of acid and zinc. So you're paying money to get rid of it, but it actually contains a lot of valuable zinc. And they've developed technology to take the zinc back out, reuse it for other high value things. So you get value from recovering the zinc, and you save cost from dumping this toxic sludge. And of course, you save environmental impact as well. So they started about 2 or 3 years ago and are doing really great things in the circular economy, which is, the idea is that instead of taking things, mining them, using them, dumping them, we're actually materials are going around in circles in our economy. And to do that, it really requires material science to figure out how to recover these materials and use them again. Another really good example along those lines is a company called Mint Innovation, which is a little bit further along their growth journey. They're based in Auckland, and they, I don't know if they coined the phrase, but it was the first time that I'd heard of it, this phrase urban mining. So they're a gold mining company, but they're mining gold in e-waste. That is crushed up old computers and things like that have got a lot of gold, as well as jewelry, which is arguably not such an important use of gold. Gold is actually really useful scientifically in electronic circuitry because it's very conductive, it's very soft, etc. So gold has technological uses. And so basically, they take e-waste, crush it up, and there's a higher concentration of gold in e-waste than there is in gold ore if you were mining gold in the environment. And so they've got proprietary technology that uses a kind of an enzyme digestion to pull out all of the gold from this crushed up slurry of e-waste. And their vision is to basically design and build little mini or micro factories that'll go in like shipping containers that can go in every city of the world to process their e-waste. Or another example, again up in Auckland, Avatana, same kind of theme, creating value from waste. So they're looking at waste from I think, which might have been from steel or something like that, steel manufacturing, and extracting things that they can make like TiO2 for paint and things like that. So they're basically taking the waste from one industry and using it with a little bit of clever chemistry to make value for something else, and ultimately save mining up, digging something else out of the ground by taking what's already there. Humblebee Bio, based in Wellington, and they have got a really novel bioplastic that is that comes from, or at least the kind of inspired by a really rare type of bee that creates this really really tough kind of plastic. It's not plastic, but a tough kind of biopolymer that's really resistant to heat and to acid and things like that. And so kind of by studying that and then figuring out ways to replicate it, the researchers have made a really kind of niche plastic for like medical technologies and things like that can also be disposed of very safely, being completely biologically derived. And one of the last examples I have is, you'll remember at the very start, I talked about aluminium ion batteries as a potential replacement for lithium ion batteries, simply because aluminium, well, first of all, it's very abundant, and it's also carries a 3+ charge. So this is actually now being spun out in the company Tasman Iron, led by Dr. Shalini Divya, based here in Wellington. So they again got investment with venture capitalists in the last year or so, and really scaling up their process, taking it from the lab to the next steps. And then I think this is my final example. Another kind of clean tech example out of Wellington is a company called Liquium that's really just spinning out right now, led by my colleague Frank Natali here in Wellington. And they discovered a catalyst that takes nitrogen and hydrogen and turns it into ammonia. And so ammonia is, you might know, is a liquid. It kind of smells like fish, but it's actually quite a useful chemical. Well, first of all, it's used to make fertilizers, but also as a means of kind of transporting hydrogen. Hydrogen's a gas, so if you can convert hydrogen into something chemically, into something that's liquid, and then convert it back again, it's actually a really good way of storing and transporting energy. So Liquium are looking at using their catalyst to generate ammonia for shipping fuels. So container ships need to carry a lot of fuel, and that could be a good way of decarbonizing the shipping industry, having them run on ammonia. So that's another one to watch. Very, very, very new spin-out company. So just to wrap up, these are the partners as introduced in the start of the MacDiarmid Institute, and here's our kind of summary statement of the MacDiarmid Institute around innovation of materials that are of importance to our sustainability. And I will leave it here with some further contact information about the MacDiarmid Institute, and I would be very happy to take questions about any of this. And I saw that there was one or two things coming on the chat, which I could start with, I guess, and others are welcome to jump in.
Well, how about I'm just going to say thank you to you first, and then we'll go with the questions, if that's all right.
Yeah,
the person that's doing the recording has to step away. Yeah, so thank you so much, Justin. Oh my gosh, that was amazing. Half an hour or slightly longer than half an hour of a whole lot of information that was really interesting. I could listen for a lot longer, but yeah, I'm really interested about the gold and the computers. I've got a couple of computers. When I'm feeling low on cash, I'm going to have to smash them up and get it all out. But the carbon, I was also interested that the carbon cost of computing is more than air travel. You know, we hear about air travel all the time, don't we, about how it's, you know, ruining the planet. But actually it sounds like maybe the remote working is also contributing to that. And my son will be really annoyed to know that hydrogen-powered cars are coming quick, because he still likes his petrol-powered car. So yeah, it's really fascinating, and it's great to know that so many New Zealand companies are getting on board and being innovative. So yeah, thanks so much, Justin, for sharing all that amazing information. We've recorded it, so it will be available for people to go back to and listen to again. So yeah, if you would like to answer some of these questions, that'd be great. Can you can see them, can't you?
Yeah, I'll just read them out and then try to answer them.
Cool.
Sure. So just going in order, aside from the black hole one, which I won't count as being in my domain, can you capture CO2 and store it away like a new version of coal? Yeah, I mean there is a effort, particularly on the geoengineers. You know, we need to capture a lot of CO2 in order to make a difference. And so people are looking at whether there's kind of underground aquifers and, you know, space under the ground that we could just pump it and forget about it. But you know, that's risky, and but it's also quite low value. Like it costs you to do that. I guess our approach is to if you capture CO2 and then develop catalysts to convert it into something else, then you're actually creating value. So it's not just a cost, but you're actually getting something out of it. So the something else could be materials like polymers. So if we're abandoning fossil fuel industry in the future, then we're going to have to find other ways of getting carbon-based chemical commodities, you know, things we use in, you know, some plastics that we might not be able to do away with, or all manner of other things. You know, anything that's synthetic carbon-based comes from petroleum, basically. So we might need to develop non-petroleum ways of making those things. But you could also actually convert CO2 back into a carbon-based fuel and use it again. And as long as you're always capturing the CO2 and converting it efficiently, then it's carbon neutral. Even though it contains carbon, if it's a closed cycle, it's neutral. So that's the other thing that you can do if you capture it. So I think, honestly, I think the best way to store CO2 is growing trees, and that's certainly, and you know, that happens. If you just plant trees, they'll grow. And I think that's a really important part of, you know, if I've had a brief look at the emission reductions plan, and one of the key things is establishing larger scale native forest planting programs, which I think is really important. So yeah, I'll move on. Sorry, going on a bit. So I'll move on to the next question. What are some of the new advances in data storage? I think a big thing here is, and this is something I could have spoken about, that colleagues in the MacDiarmid Institute are working on, is so-called spintronics. So instead of electronics, where the information flows by movement of electrons, you can really efficiently move and store information by the flow of electron spins. So electrons, they actually kind of orbit, and they could be orbiting that way or that way. And so that's your kind of 0 or 1, if you like. But it's actually really efficient to manipulate spins. And so we've got quite a big spintronic research program. And this is just one of many new frontiers in data storage. But just like energy storage, data storage kind of goes hand in hand with data processing. The next question here is, will hydrogen eventually replace natural gas in the domestic market? It's quite possible. I mean, I don't know either way. Certainly there's a lot of research going on. There's trials, for example, trialing blending hydrogen with natural gas. And I think, you know, up to 20% hydrogen, it works really well and it doesn't break anything. But if you just went to 100% hydrogen in the national network, it's not going to quite work. You of course need a green source of hydrogen. You don't want to take that hydrogen from natural gas in the first place, which is actually where it comes from in most parts of the world. But the other thing I think that's worth watching is biogas. So kind of making natural gas from fermenting bio waste, just from landfills or whatever. So yeah, I think we'll want to make use of the natural gas infrastructure that we have, and use other kind of gas-based fuels, whether it's hydrogen, biogas, or whatever. The next question here is around plastic photovoltaics. So the question is that light is notoriously hard on plastic. So what are the flexible photovoltaic strips made from, and how long do they last? Yeah, that's a good point. Light, if you have bits of plastic, say garden furniture that are left out, they turn white over time, and especially in New Zealand, it's actually the UV that does that, because UV light is really high energy, and it's got high enough energy to kind of rip out electrons and make it's all radical chemistry. So these photovoltaics, they generally have a kind of a UV filter on them, so that the UV is not getting into the actual active material, because otherwise it would degrade it. And they do, I mean, that still the question of how long they last is an active research question. They actually last a lot longer than most people think. So when you look at them, you think that they'll probably last for a few weeks or months, but they actually last for, when they do accelerated aging testing, which is test their efficiency in a really hot, humid environment where it kind of simulates, over the course of a few months, you could kind of get the equivalent aging to a few years in the open environment. So they kind of extrapolate how long they'll last for, and the latest estimates are something like 8 years, which is not quite the 20 to 30 years that you need for kind of building materials. But it's certainly long enough to be of value if they're very cheap to manufacture. But that's absolutely an active research area, just the longevity of these materials. Next question, is there copper in computers, and is it worth recovering? Probably. And these urban mining kind of operations, they are researching, gold was their starting point, but they're looking at ways of recovering everything. I mean, ultimately you want to just recover everything, and have a truly circular economy. Along those lines, actually, there's research into getting lithium out of seawater. Instead of mining lithium from the ground, there is actually lithium in the sea. It's just very dilute, but as long as you've got a really efficient way of collecting it, then that could be a very sustainable way of supporting our EV industry. So the final question here is, I've heard the ocean stores a lot of carbon as well as releasing it into the atmosphere. Can we learn how to remove the stored carbon from the ocean as we reduce atmospheric carbon? So yeah, that's one question. So that's definitely true. There's a lot of carbon stored in the ocean, and from my understanding, and I'm not an environmental scientist, this is very strongly connected to the temperature and the acidity of the ocean. But basically, the ocean will, it will, if there's more carbon dioxide in the atmosphere, it will petition into the ocean as well. But I think that there's not really anything that we can do and probably it's at a scale that we shouldn't even try to manipulate the ocean in that way, because it will probably have knock-on effects. But I don't think there's anything that we can actively do to force CO2 into the ocean. But I think that in terms of the whole biosphere, probably planting more trees is something that is within our within our control. And, you know, and at steady state, I think there should be a lot more biomass in trees, and certainly pre-humans, there was a lot more trees. But that's not a forever solution. We still need to get into we still need to have a steady state where we're emitting, where we're not net emitters. So planting a lot of trees, you know, if we could do that really quickly, that will suck up a lot of CO2. But once you've actually got established forest, you're not actually, you've kind of sucked up all the CO2 that you can get, if you know what I mean. So it's something that's essential to do, but it goes alongside reducing our emissions or eliminating our emissions. And then the final question here is, if we can produce water as a byproduct, can we use those processes to offset low availability of water in arid conditions? Yes. So, for example, burning hydrogen to get energy with water as a byproduct. I guess the thing is, there's not a lot of water. So I once did a calculation, I wish I could remember the details, but just the amount of energy, let's say in, I don't know, the amount of, if you filled your car with hydrogen and drove to Auckland, the amount of water that you would get as exhaust is pretty tiny. It would probably be, I don't know, like a bucket or something like that. I'd need to revisit that calculation, but I once calculated how much energy, like if you took an Olympic swimming pool and converted it to hydrogen, how much energy that would give you. And I apologize that I don't remember, but it was a huge amount. So the energy density in the hydrogen water is huge. So it's not going to be anywhere near enough water to, you know, fertilize deserts or things like that. But certainly it's clean water. So, so you know, it should be used for something.